Okay, so this is actually a nice clip illustrating the TNB frame of reference. I'm gonna actually put the link. I didn't make this animation, but it's a very nice one that I found on YouTube. I'll put the link in the description of this video. So the let's start actually from the beginning here. So the red one is the unit tangent vector, the green one is the normal, and the binormal, like I said, keeps track of the orientation, toes ahead. If you imagine that you are the person working on the curve, or if it's a mobile, it's a direction from the floor to the ceiling if you want. And as the point moves on the curve, this frame of reference moves with the point itself, indicating the particulars of this motion, right? So notice that how the green vector always indicates the direction of the turn. And that also includes twisting, right? So we are in 3D. So when we say change in the direction of the turn, that's not just in a plane, right? I mean, you could have, for example, a full twist. And if you don't see actually how the TNB frame of reference changes, you wouldn't be able to notice just by the shape of the curve, right? I mean, the curve itself is like the road, essentially, but the frame of reference, the TNB frame of reference, actually tells you how the object moves on that road, so to speak. So that's how this frame looks like in motion. And let's actually go back to the example, some of the example we did before with Maple. Spend some time on that part. So make sure, if you use Maple, make sure you actually load both vector calculus and plots to access these commands. And let's talk about the curvature first. This is one of the examples that I did with for computing the curvature at the point 1 and 5, right? When I told you that you could actually have told beforehand that the curvature at 1 is higher, because as t increases, the curve is very stretched, so there's very little turn later on as t increases. So as you can see here, as t increases, the curve is very stretched upward, because I made it so that the z coordinate increases much faster than the other coordinate. So obviously the curvature at 1, earlier here, the domain I chose here is 0, 6. So in the beginning of the motion, it's far more turning compared to the distance traveled than later on. How do I actually do it with Maple? Well, as it turns out, many of these objects are already predefined in Maple. So Maple also accepts the vector in the traditional notation in the notation in the book with less than or greater than brackets, to indicate the vector function. Just make sure you load it as a function. And then there is a tool called Curvature, which is self-explanatory. It actually computes the curvature in terms of t in general. And then you can just evaluate it at the point in question, right? So let's say I want to evaluate it at 1. We did this on paper. We need to approximate, so it's approximately 0.08. At 5, let's evaluate the same thing at 5, and much smaller value, approximately 0.0004. Let's talk about the tangent normal by normal. In Maple, there's a tool called principal normal. Be aware that's actually not normalized. It just gives you the derivative of the unit tangent, basically. So let's load an example. I think this is the example I did in class in the notes. Either way, doesn't matter. Principal normal gives you the like I said, the normal, but not normalized, not of length 1. There is a command called normalize, which will normalize any vector. So just to see how that functions, if I say normalize the vector 1, 1, 2, it will give me, let me actually, let me see if I can make an easier one to follow. It'll give me the normal, so 1, 1, 1, right? So the length is 3, 1 over 3, 1 over 3, 1 over 3. it's written as root 3 over 3, but it's the same thing. Notice that maple, let's make this a little bit bigger here. Maple indicates the standard unit vectors ijk with ex, y, ez. That's just another notation here in maple. But anyway, these are the units, the standard vectors, standard unit vectors ijk. So it gives you the answer as a combination ijk, but these are the components. So going back to the principal normal, if you want to find the actual unit normal, call the principal normal command and then inside the normalize command. So we did this, we didn't load the function, sorry. Let me load the function here. Normalize principal normal. Doesn't recognize the, I think I know what goes on. I have to call n of t separately. There you go. It's another annoying thing with maple. You need to call the function. It doesn't display the execution of the functions by default. It doesn't know the domain for t, so let's tell maple that this is this deals with real numbers. Let's see, in the simplify, assuming real, there you go. Gotta tell maple that these are real numbers. So this is the n of t. It's simplified in a different form, but if you check it with your notes in the previous part of this lesson, it should be the same thing. It's simplified a little bit different than what I did. So anyway, that's the unit normal. For the unit tangent, let's do it step by step. R prime of t, 1t, 2t. Normalize it. That gives me the unit tangent. Let's call it separately here. There you go, the unit tangent. And since we're in maple here, we can ask maple to do the cross product in terms of t, which is obviously tedious by hand, right? So cross product, again, tell maple that is, you're assuming simplified and assuming real numbers. So simplify. And it so happens in this case that actually it doesn't depend on t at all. I mean, it simplifies to the same binormal. So tangent, the unit tangent, unit normal happen to depend on t. Normally binormal also depends on t, but it doesn't have to. Sometimes it simplifies. I mean, in the other words, the orientation of the binormal is given by the same vector all the time. So I think that's it for this presentation. Obviously, if you use a different computer algebra system, the commands might look different, but they should be implemented one way or another. So that's it for today.